every attempt to reach the coldest possible temperature has revealed something unexpected. Even when atoms are pushed to within billionths of a degree above absolute zero, a thin trace of motion refuses to vanish, as if nature is holding on to one final layer of activity. The limit is well defined: 0 Kelvin, minus 273. 15 degrees Celsius. Yet experiments from early helium studies to the data gathered by NASA's Cold Atom Lab on the International Space Station have shown that the last step toward perfect stillness never arrives. This trail of evidence leads into a region where zero-point energy becomes measurable, where the quantum vacuum shapes behavior, and where Bose-Einstein condensates reveal structures that appear only when matter is cooled almost as far as physics allows. And in Part 1, what if absolute zero isn't stillness at all? The story turns to that remaining motion, the part no experiment has yet been able to remove. Something deeply counterintuitive appears the moment matter approaches minus 273, 15 degrees Celsius. Motion that should disappear never truly fades. Across nearly a century of laboratory work, from the cryogenic chambers built in the 1930s to NASA's Cold Atom Lab operating aboard the International Space Station, instruments keep registering a residue of activity that classical physics expected to vanish. Absolute zero is defined as 0 Kelvin, the theoretical point where thermal motion reaches its minimum. Early researchers assumed that reaching this boundary would freeze every degree of freedom. Yet every attempt to cool atoms toward that limit produced a different story. When experimenters lowered the temperature of helium with liquid air precoolers in the 1930s, they noticed that helium-4 refused to behave like a solid under normal pressure. Instead of forming a rigid lattice, it remained liquid, showing a level of internal motion too stable to dismiss as experimental error. By the 1950s, advances in refrigeration, especially the development of dilution refrigerators using helium-3 and helium-4 mixtures, allowed scientists to reach temperatures in the millikelvin regime. At these depths, thermal motion should have collapsed into near silence, yet magnetometers and pressure sensors still recorded activity. The readings were small but reproducible, and multiple laboratories confirmed them. This consistency indicated that the remaining motion was not noise, but a baseline built into the structure of matter. The explanation arose from quantum mechanics. In that framework, a particle cannot have both a perfectly defined position and perfectly defined momentum. Werner Heisenberg described this in direct terms. Uncertainty is built into the world, not into our measurement. This principle ensures that even at the lowest achievable temperature, atoms retain a minimum amount of kinetic energy known as zero-point energy. Evidence for this principle appears repeatedly throughout 20th century physics. One of the clearest examples came from work by Willis Lamb and Robert Rutherford in the 1940s. While studying hydrogen, they detected a tiny shift in the energy levels of the atom, a shift later attributed to fluctuations in the quantum vacuum. These fluctuations, though invisible to the eye, exert enough influence to modify energy states. Lamb received the 1955 Nobel Prize for this discovery, and the effect remains a landmark demonstration that empty space is not motionless. Further insight came from experiments involving photons trapped inside ultra-cold cavities. Physicists found that even when these cavities were cooled close to absolute zero, photons continued to appear in discrete packets. This behavior was consistent with predictions from quantum electrodynamics. Vacuum fluctuations stimulate spontaneous emission, producing detectable radiation even in near-perfect cold. Such findings revealed that absolute stillness cannot exist because the vacuum itself contains energy that cannot be removed. By the early 21st century, the next leap came from microgravity studies. In 2018, NASA launched the Cold Atom Lab, CAL, a facility designed to create some of the coldest environments ever produced. CAL regularly achieves temperatures only a few nanokelvin above 0 Kelvin. In microgravity, atoms remain suspended rather than settling, allowing long observation times. Inside this platform, clouds of rubidium and potassium atoms displayed patterns of motion that persisted no matter how deeply they were cooled. Researchers identified these patterns as signatures of zero-point energy, the lowest energy state permitted by quantum mechanics. These observations reinforced a principle long suspected. Absolute zero is unreachable not because of technological limits, but because physics forbids a total removal of energy. The third law of thermodynamics states that reaching 0 Kelvin would require an infinite sequence of steps. As a system approaches this temperature, its entropy, the number of ways its particles can be arranged, collapses. Removing the final bit of energy becomes increasingly difficult until the remaining amount is protected by the fundamental structure of quantum fields. This principle becomes especially clear when examining the behavior of helium 3 inches dilution refrigerators. As temperature decreases, the specific heat of helium-3 falls sharply. Yet it never reaches zero. Cooling slows dramatically because the remaining energy is tied to quantum states that cannot be erased. The material does not freeze. Instead, it transitions into exotic phases governed entirely by quantum rules. Ultra-cold atom experiments illustrate the same idea. When a cloud of atoms is confined in a magnetic or optical trap and cooled to microkelvin temperatures, thermal motion fades, allowing the quantum wave function of each atom to become dominant. Imaging techniques developed at laboratories such as MIT and CERN reveal that these clouds do not become static. Instead, they display interference patterns that shift according to momentum values inherent to the atom's lowest energy states. A particularly illustrative method is time-of-flight imaging. When the trap holding an ultra-cold cloud is suddenly turned off, the atoms expand. If they were motionless, the cloud would remain compact. Instead, it spreads in a predictable pattern, demonstrating that each atom carried residual momentum. This effect is a direct consequence of the Heisenberg uncertainty principle and has been reproduced in laboratories around the world. Even the behavior of light supports this view. Studies at Caltech involving cavity QED examined photons confined in ultra-cold reflective chambers. These photons persisted with quantized momentum values, even at temperatures approaching absolute zero. Kip Thorne once phrased it plainly: space-time tells light where to go. The motion of photons inside these cavities does not come from temperature. It arises from the structure of space-time and the electromagnetic field itself. The broader cosmos offers its own confirmation. ESA's Planck mission produced one of the most detailed maps of the cosmic microwave background, showing that the universe currently sits at about 725 Kelvin. As the universe expands, this temperature decreases, but according to models of cosmology, it approaches zero asymptotically without ever reaching it. Even on scales spanning billions of light-years, complete stillness is out of reach. The entire universe carries an underlying level of motion produced by quantum fields that permeate space. When all of the measurements are placed side by side, a clearer picture forms. Absolute zero is not a point where physics fades away. It is a temperature where classical motion stops being the correct description and quantum structure begins to dominate the behavior of matter. As atoms are cooled toward this limit, features normally hidden at higher temperatures become measurable. Discrete energy steps, contributions from the vacuum, extended wave-like distributions, and phases that move without resistance. The colder the system becomes, the more its underlying framework comes into view, revealing motion that no conventional removal of heat has been able to eliminate. From here, the path continues into part 2. Why do atoms keep moving even when all heat is gone? Where that remaining motion is examined in detail. The most startling discovery in low-temperature physics appears the moment helium approaches 0 Kelvin. The motion that our equations insist should fade into silence continues, with a stubborn rhythm that no technique can suppress. Researchers pushed the temperature lower with evaporative cooling, magnetic traps, and laser-based slowing, yet every method pointed to the same truth. The atoms refused to become motionless. This behavior confused early experimenters. When helium-4 was first cooled inside precision cryostats during the mid-20th century, instrumentation captured a persistent jitter far below what classical thermodynamics allowed. The phenomenon was too consistent to attribute to mechanical vibration. It appeared across continents, across decades, across upgraded equipment. Scientists recognized something deeper was unfolding, something they had already seen hinted in the mathematics of the quantum world. Werner Heisenberg had described a limit that no amount of laboratory ingenuity could bypass. He wrote that uncertainty is built into the world, not into our measurement, a statement that carried consequences far beyond theory. In the quantum description of nature, position and momentum cannot both be pinned down perfectly. Reducing one always increases the spread of the other. If helium atoms were cooled into a state with almost no kinetic energy, their positions would have to become sharply defined. That would violate the rule. To preserve the structure of the microscopic world, a minimum level of motion must remain. This minimum is known as zero-point energy. It is not a leftover from machinery or environmental interference. It is part of the architecture of the quantum field that defines each particle. The helium atom carries vibrational modes and internal degrees of freedom that cannot sink below this baseline. No refrigerator can remove it. No magnet can confine it out of existence. One of the earliest illustrations of zero-point energy emerged during pioneering helium work at Leiden in the early decades of the 20th century. Technicians cooled liquid helium using pumped vacuum lines that dropped the pressure until the temperature slid toward the single-digit Kelvin range. Even there, where thermal motion should weaken into near silence, helium-4 displayed fluid behavior that surprised those observing it. The atoms glided with unusual ease, forming patterns that did not resemble the expected approach to a rigid state. Laboratories in the United States and the Soviet Union reported similar results. The stubborn motion had become a serious research target rather than an experimental curiosity. The path toward clarity accelerated when superconducting detectors entered the field. These sensors, sensitive to magnetic fluctuations far smaller than what classical equipment could detect, recorded recurring signatures of movement inside helium samples near absolute zero. The atoms behaved as if they were caught in a system of standing waves. Temperature was not driving this behavior. The presence of quantum rules was. By the 1990s, laser cooling opened a new frontier. Beams of light tuned precisely to atomic transitions slowed helium atoms by absorbing and re-emitting photons. Each absorbed photon reduced the velocity of the atom by a measurable increment. Laboratories at MIT, NIST, and Stanford built intricate arrangements of counter-propagating beams to remove as much momentum as possible. The atoms slowed drastically, dropping into the micro-Kelvin regime. Yet the baseline jitter remained. To understand why, imagine helium trapped in a shallow, bowl-shaped energy landscape. Cooling the atoms removes heat, allowing them to sink lower in the bowl. But unlike a marble that can roll to the bottom and stop, the helium atoms cannot occupy a condition that assigns them both a fixed position and no momentum. Zero-point energy keeps them suspended above absolute stillness at a level set by the curvature of the energy landscape. This principle became clear through the study of superfluid helium. When helium-4 is cooled to about 2 Kelvin, it transitions into a state where viscosity disappears. A thin film of the liquid climbs container walls. Once set into motion, the film circulates indefinitely without slowing. Researchers realized that this feature required the presence of long-range quantum order, something that could only exist if the atoms retained minimal motion, even in extreme cold. If the atoms truly stopped, the coherent properties of the superfluid would collapse. Neutron scattering experiments reinforced this view. By directing beams of neutrons through ultra-cold helium, physicists at institutions such as Oak Ridge National Laboratory measured the recoil patterns that indicated how quickly atoms were moving. Even when the helium sat within a fraction of a Kelvin above zero, the scattering angles showed a spread of momentum consistent with zero-point activity. The atoms could not be forced into stillness because stillness was not one of the allowable quantum states. The same principle governs electrons bound within solids. Semiconductor laboratories cooled silicon and germanium samples to millikelvin temperatures and probed them with microwave radiation. Electrons shifted energy levels in ways that pointed to persistent motion. Researchers concluded that each electron occupies quantum states defined by probability distributions that cannot be sharpened into an unmoving point. These experiments supported the wider conclusion that all particles, not only helium, retain motion dictated by the underlying fields of nature. A more recent chapter came from NASA's Cold Atom Lab, CAL, aboard the International Space Station. Microgravity allows atoms to float rather than sink to the bottom of a trap, offering extended observation without gravitational compression. Inside CAL, atomic clouds of helium, rubidium, and potassium reached nanokelvin conditions. Even there, precision imaging revealed wave-like distributions that widened and contracted according to the rules of quantum mechanics. Scientists studied how these clouds expanded when released from their traps. If the atoms were motionless, the cloud would remain tightly clustered. Instead, the cloud expanded with characteristic patterns that corresponded to zero-point motion. The cold removed thermal activity, but it also exposed the quantum identity hidden beneath it. The effects of zero-point energy also appear in the electromagnetic field. When two reflective plates sit extremely close together, the vacuum between them displays measurable forces. This phenomenon, called the Casimir effect, arises from fluctuations that persist even at temperatures near absolute zero. Laboratories at the University of Washington, MIT, and institutions across Europe have verified this force with increasing precision. It demonstrates that fields throughout space retain intrinsic activity regardless of temperature. Matter is not the only participant in this persistence. The vacuum itself contributes. These discoveries connect with another area of research. ESA's Planck mission studied the cosmic microwave background, a radiation field that fills the universe. The temperature of this background today is about 725 Kelvin. As the universe expands, this temperature decreases, but cosmological models indicate that it approaches zero without reaching it. The entire cosmos carries residual energy defined by quantum fluctuations. Across billions of light years, the same rule holds. The world does not reach perfect rest. Behind each milestone lies a human story. Early helium researchers labored for hours adjusting valves by hand, relying on fragile thermometers that offered only coarse readings. When unexpected fluctuations appeared, they tightened fittings, recalibrated sensors, and even rebuilt apparatuses from the ground up. The anomalies survived every adjustment. That persistence signaled that nature, not equipment, was speaking. Later generations equipped with advanced superconducting sensors repeated the experiments with greater precision. The same patterns returned. CAL researchers, operating in orbit, extended these observations into microgravity, proving that even the cleanest possible environment retains quantum motion. The reason is woven into the framework of quantum fields. Every particle exists as an excitation of an underlying field. These fields are never flat. Even in their lowest energy configuration, they contain vibrations. Cooling matter does not eliminate those vibrations. It only removes contributions from heat, leaving behind the unavoidable flaw set by the field. Zero-point energy does not represent a failure of cooling methods. It represents the minimum allowed by the architecture of nature. This realization shifts the way the coldest regimes are interpreted. Instead of approaching a final halt, the progression into lower temperatures exposes layers of structure that cannot be seen at higher energies. Atoms begin forming coherent states. Electrons settle into energy bands determined by the geometry of the surrounding fields, and helium enters superfluid phases governed by fully quantum behavior. These motions are no longer set by heat. They arise from the rules that dominate at microscopic scales. As evidence from laboratories, theoretical models, and space-based measurements converges, a broader landscape comes into view, extending the investigation toward conditions where motion might be reduced even further. From there, the story moves into part 3. Could the universe ever allow a perfectly motionless particle? Where the limits imposed by quantum structure become the next point of focus. One of the most striking results in cryogenic physics appeared when electrons inside ultra-cold semiconductors refused to settle into perfect rest, even as temperatures approached the lowest values attainable in a laboratory. Experiments carried out at Los Alamos National Laboratory showed that when the lattice of a semiconductor was cooled to millikelvin levels, electron motion persisted in patterns that could not be explained by heat. The activity followed a spread of momenta predicted only by quantum mechanics, indicating that even the quietest conditions still contain motion defined by the particle's quantum state. Researchers began by fabricating semiconductor samples with exceptionally high purity. Impurities inside the material would have masked the delicate signals they sought. The goal was to push electrons into their lowest possible energy bands and watch how they behaved when the surrounding lattice lost nearly all thermal vibration. Conventional expectations predicted that electrons should settle into fixed positions within the crystal's potential landscape. Instead, precise spectroscopic measurements revealed that each electron maintained a distribution of momentum as if pinned to a rule deeper than temperature. The discovery echoed a principle long embedded in quantum field theory. Particles do not exist as isolated objects. They arise as excitations of underlying fields that permeate space. These fields cannot be completely motionless. If they were, electrons, quarks, and photons would have no ability to propagate or interact. The experiments at Los Alamos did not simply observe stubborn electrons. They revealed the behavior of the fields themselves. Early evidence for this principle first emerged in the 1950s when solid-state physicists cooled germanium and silicon samples and performed microwave resonance experiments to probe their electronic structure. Even at temperatures of a few Kelvin, resonance lines displayed broadening consistent with quantum motion rather than thermal agitation. Over the following decades, laboratories improved the resolution of their detectors, reaching sensitivities capable of measuring frequency shifts governed by the smallest changes in energy levels. Each improvement reinforced the same conclusion. Electrons never came to a full stop. This became clearer when techniques such as Shubnikov-de Haas measurements were applied. In these experiments, high magnetic fields were combined with ultra-low temperatures to examine how electrons moved in quantized orbits. If electrons could reach perfect rest, the quantized steps would disappear. Instead, the steps appeared with astonishing clarity. Their very existence required electrons to retain baseline motion derived from the geometry of their quantum states. Similar patterns emerged in research involving two-dimensional electron gases, systems created within semiconductor heterostructures. When cooled below 1 Kelvin, these systems display mobility far higher than their three-dimensional counterparts. Cyclotron resonance experiments used terahertz radiation to probe the electrons' paths. The data showed that even at ultra-low temperatures, electrons behaved like waves with finite spatial extent. Their momentum could never narrow into a single value. The quantum field that defines them imposes a lower bound. This lower bound has consequences across particle physics. Quarks, for example, cannot exist in isolation. They remain confined inside protons and neutrons, held together by the strong force. Within these bound states, quarks possess momentum distributions that do not flatten to zero. Measurements from deep inelastic scattering experiments, conducted using high-energy accelerators, show a spread of momenta even when the net energy of the system is minimized. The quarks remain in motion because the quantum field that binds them forbids perfect stillness. Photons, too, demonstrate a related principle. In optical cavities cooled near absolute zero, researchers at MIT and Caltech observed photons that continued to appear in discrete packets. This behavior did not depend on temperature. It depended on the ground state of the electromagnetic field. Kip Thorne once explained that space-time tells light where to go. The direction and momentum of photons inside a cavity follow the curvature and boundary conditions of the field. No amount of cooling can erase the motion defined at that level. These findings form a consistent picture when viewed through the lens of quantum field theory. Each particle is described by a wave function that spreads across space. Attempting to confine a particle into a state with no momentum would require compressing its wave function into an infinitely small region. Such compression would force the particle's momentum to become infinitely uncertain. The universe avoids this contradiction by imposing a minimum level of activity. The motion persists because the wave function cannot collapse into a motionless point. Behind these observations lies a long tradition of experimental refinement. At Los Alamos, engineers designed cryogenic stages with vibration isolation platforms to ensure that external disturbances did not contaminate the data. Sensors were shielded with superconducting materials to eliminate magnetic interference. Teams performed repeated calibrations at each temperature plateau to verify that the observed electron activity remained consistent across multiple cooling cycles. Every safeguard was implemented to remove alternative explanations. The results endured. Other institutions extended this research. At the National High Magnetic Field Laboratory in Florida, electrons in semiconductor samples were pushed into quantum Hall regimes. These regimes form when electrons move in tight circular paths defined by magnetic flux. Their behavior is so dependent on underlying quantum laws that deviation from the expected patterns would immediately signal a breakdown in theory. Yet the patterns remained stable even when the temperature dipped to tens of millikelvin. The electrons could not be forced into a condition with zero kinetic energy. The implications reached beyond condensed matter physics. ESA's missions that mapped cosmic radiation observed that even the microwave background, the oldest detectable light in the universe, carries tiny fluctuations that reflect the quantum origins of the early cosmos. The temperature of this radiation is now approximately 725 Kelvin. According to cosmological models, it will continue to decrease as space expands. But none of these models allow it to reach a perfect zero. A faint residue of energy persists throughout the universe. The same principle that sustains motion in electrons governs the cosmos at large. Historical accounts show how deeply this idea influenced scientists. When researchers first observed the unexpected electronic behavior in cryogenic semiconductors, they questioned every component of their apparatus. Some suspected mechanical vibrations. Others blamed electromagnetic interference. Teams replaced wiring, rebuilt cooling stages, and repeated measurements across different laboratories. With each replication, the signals remained. At that point, the community began recognizing that the observed motion was not an experimental artifact, but a fundamental feature of particle behavior. The more these results accumulated, the clearer the picture became. Stillness is not physically attainable because it conflicts with the rules that shape quantum fields. A perfectly motionless particle would violate the relationship between position and momentum that forms one of the central pillars of quantum mechanics. Even the smallest known constituents of matter obey this rule. Quantum fields cannot flatten into silence. The universe sustains a baseline activity woven into the foundation of nature. The progression into lower temperatures reshapes the meaning of cold. Lower temperatures do not bring particles to a stop. They remove the thermal activity that masks the structure underneath. What remains is motion set by fields, symmetries, and quantum rules that stay present even when heat is almost fully removed. In this range, atoms and electrons display behaviors that never appear at higher energies, revealing the framework that supports their motion rather than suppressing it. With this foundation established, the direction naturally widens toward the properties of light at these extremes. Setting the stage for Part 4, does light itself possess a resting state near 0 Kelvin? The moment physicists cooled electromagnetic cavities toward the lowest temperatures their instruments could achieve, something unexpected appeared in the data. Even when the walls of those cavities reached microkelvin conditions, photons escaping from within still carried momentum in clean, unmistakable units, as if light itself could not recognize the idea of rest. This observation first took shape in laboratories at Caltech during early cavity quantum electrodynamics work. Researchers constructed reflective chambers designed to trap photons and cool the interior environment until the remaining thermal background became almost negligible. If light behaved like a classical particle, those photons should have lost their motion as the temperature approached 0. Instead, photodetectors placed at the cavity's output registered discrete energy packets, moving with unchanged precision. The photons acted as though temperature had never been part of their identity. This pattern matched theoretical ideas that had emerged decades earlier. In general relativity, light follows the structure of spacetime, not the influence of temperature. Kip Thorne phrased it clearly when he said, "Spacetime tells light where to go." That guidance does not weaken when matter is cold. Light maintains momentum because the electromagnetic field that generates photons possesses quantized modes, and no degree of cooling can suppress the foundational geometry of those modes. To understand how scientists recognized this, it helps to trace the path of early cavity experiments. In the 1970s, researchers began building superconducting cavities with extremely high reflectivity. These devices confined photons long enough to measure how their behavior changed under different environmental conditions. When cooled below 1 Kelvin, the cavities reduced thermal radiation to extremely low levels. Yet the frequency of the trapped photons did not drift downward. Data showed that each photon maintained a precise relationship between its energy and its momentum. That behavior could not arise from temperature. It came from the quantum field defining the photon itself. As technology advanced, physicists refined their ability to measure zero-point fluctuations inside these cavities. Zero-point fluctuations refer to the smallest allowed excitations of the electromagnetic field, present even when no classical radiation is introduced. At Caltech, MIT, and institutions across Europe, experimental teams found that cavities cooled to microkelvin temperatures still exhibited spontaneous emission events triggered by the vacuum's intrinsic activity. Sensors detected photons emerging without any external driving. These photons reflected the lowest possible excitations of the field, demonstrating that even at minimal temperature, the vacuum contains energy that cannot be removed. One of the landmark demonstrations came from experiments examining the Lamb shift, the small difference in energy levels within hydrogen atoms. This shift was influenced by the fluctuating electromagnetic field surrounding the atom. When researchers isolated these atoms inside ultra-cold environments, the Lamb shift remained. That persistence revealed the nature of the field. The vacuum cannot fall into complete stillness because its lowest energy condition includes motion encoded by quantum rules. The story deepened as new detectors improved sensitivity to single photon events. NASA's Cold Atom Lab, orbiting aboard the International Space Station, offered an environment free from gravitational compression. Although the lab's main purpose was to study ultra-cold atoms, several experiments relied on precise optical cavities to measure how photons interacted with atomic clouds at nanokelvin temperatures. These observations validated a key prediction. Even when matter cooled to one of the coldest recorded states in the universe, photons interacting with that matter retained momentum governed by electromagnetic field structure, not by heat. Understanding this requires looking at how photons form. A photon is not a small object floating through space. It is a quantized disturbance in the electromagnetic field. That field has allowed modes, similar to standing waves on a stretched string. Each mode carries a specific energy and momentum. When a photon occupies one of these modes, its behavior is defined by the geometry of the field. Cooling the environment reduces thermal excitations, but it does not change the fundamental boundaries of the field. In this sense, the photon inherits its properties from the field's structure. This became clearer through research on the dynamical Casimir effect. When mirrors in a cavity move at extremely high frequencies, they can convert vacuum fluctuations into real photons. Several laboratories, including groups working in superconducting circuit systems, observed this effect experimentally. These photons emerged even when the temperature of the system was kept close to absolute zero. The effect showed that the vacuum contains energy measurable at laboratory scales and that motion in the boundary conditions of space-time-like fields can generate observable light. Further insight emerged in optical lattices, where cold atoms arranged in periodic arrays interact with photons in highly controlled ways. Researchers noticed that photon scattering patterns remained consistent across a wide range of temperatures, including the lowest ranges achievable. Momentum exchanges between atoms and photons matched theoretical predictions derived from quantum field geometry, not from the absence of heat. No amount of cooling produced a condition where photons entered a state without momentum. These results had implications beyond laboratory physics. Observations from ESA's Planck mission, which mapped tiny variations in the cosmic microwave background, showed that even the oldest radiation in the universe carries momentum shaped by early cosmic conditions. As the universe expands, this background cools, but its photons remain in motion. Their wavelengths stretch, but they never settle into rest. They trace the evolving geometry of space-time across billions of years. Historical accounts reveal how strongly these discoveries influenced scientific thinking. Early cavity researchers questioned whether their equipment introduced unwanted noise. They replaced mirrors, rewired circuits, improved thermal shielding, and even rebuilt entire cryogenic stages to ensure the purity of their measurements. Yet every improvement reinforced the same result. Photons did not lose momentum. Light acted as though rest were a forbidden state. As researchers compared notes across institutions, it became clear that the behavior reflected a universal rule. This rule aligns with the mathematical description of the electromagnetic field. Each field possesses a minimum energy that cannot be reduced to zero. Even in the lowest possible configuration, oscillatory behavior remains. Removing this motion would require the field to collapse into an undefined state, violating the relationships that allow energy and momentum to exist at all. Stillness is not compatible with the field structure. The result is deeper than the behavior of photons alone. It reaches into the foundation of how nature constructs the particles we observe. Photons cannot stop, because stopping would require erasing the modes of the electromagnetic field. Those modes define the photon's character. Cooling may remove thermal noise, revealing cleaner measurements, but it does not alter the field's geometry. Light carries momentum, because the structure of spacetime does not allow otherwise. This understanding shapes how physicists describe the coldest regions of the universe. In dense molecular clouds, where temperatures fall to tens of Kelvin, photons emerging from rotational transitions still display discrete energy steps. Instruments such as the Atacama Large Millimeter Array detect these signals across interstellar distances. Even where matter cools to near its natural minimum, light retains measurable motion. In the far reaches of space, where the temperature of the cosmic background slowly declines as the universe expands, photons continue to travel across cosmic distances, carrying information about the geometry of the cosmos. They do not slow or fade into stillness. Their momentum decreases as their wavelength stretches, but they never enter a state of rest. The structure of spacetime sets the rules they follow. The results emerging from laboratory cavities, astrophysical measurements, and theoretical models create a consistent picture. Light has no resting state. Photons exist only in motion because the electromagnetic field and the geometry of spacetime leave no configuration in which they can remain fixed. With that conclusion established, the perspective widens toward matter in its most collective form, leading into Part 5, is a Bose-Einstein condensate the closest we've ever come to true stillness? The moment scientists cooled a cloud of rubidium atoms to a fraction of a microkelvin in 1995, something unfolded that no earlier experiment had ever revealed. Instead of behaving like millions of separate particles, the atoms collapsed into a single quantum wave, a unified state spreading across the trap as though nature had merged countless identities into one. Yet even here, where temperatures approached the coldest conditions ever produced, the experiment did not uncover silence. It uncovered coherence, a collective form of motion that carried its own structure and rhythm. The first Bose-Einstein condensate emerged from the work of Eric Cornell and Carl Wieman at GILA, a collaboration between the University of Colorado and NIST. Their laboratory used a combination of laser cooling and magnetic trapping to reach temperatures below 200 nanokelvin. Laser beams slowed the atoms by repeatedly nudging them in opposite directions, reducing their velocity until thermal motion nearly disappeared. The magnetic trap then held the atoms in a bowl-shaped potential. When the temperature fell past a critical threshold, the atoms no longer occupied individual quantum states. They merged into a single macroscopic wave function, a state predicted in the 1920s by Albert Einstein and Satyendra Nath Bose. Cornell later described the moment with a line that captured the essence of the discovery. "We didn't stop the atoms, we taught them to move together." His observation pointed to the heart of the condensate. It was not an absence of motion. It was a reorganization of motion into a coherent pattern. This behavior contrasted sharply with what classical physics would have predicted. At such low temperatures, matter should settle into stillness. Yet in a Bose-Einstein condensate, the atoms behave as a single quantum entity, spreading out in a wave-like pattern that covers the entire trap. The wave function that describes this state has a well-defined phase, meaning the atoms share a unified style of motion, not an absence of motion. As imaging techniques improved, the structure of the condensate became clearer. When researchers switched off the magnetic trap and allowed the condensate to expand freely, the cloud grew in a smooth, symmetric shape that reflected the momentum distribution of the unified state. If the atoms were motionless, the cloud would not expand. Instead, it formed interference fringes that demonstrated the condensate's underlying wave nature. A story from the early days of BEC research illustrates how profound the discovery felt within the scientific community. When the first condensate formed, The image captured on the detector showed a dense central peak surrounded by faint thermal atoms. Teams gathered around the printout, verifying that the peak represented a coherent quantum state, not an artifact. As they repeated the experiment, the peak became clearer. By the third attempt, there was no doubt. A new phase of matter had appeared. Later experiments extended these insights. Wolfgang Ketteler at MIT demonstrated interference between two separate condensates. When allowed to overlap, the condensates produced a pattern of alternating bright and dark bands. This fringe pattern proved that two condensates acted like waves with defined phases. If either condensate had been motionless in the classical sense, no interference could have formed. Instead, both carried coherent quantum motion. The condensate also revealed how quantum statistics shape matter at low temperatures. Atoms in the condensate are bosons, particles that prefer to share quantum states rather than avoid them. As the system cools, more atoms fall into the lowest available state, amplifying the coherence. The process does not stop because temperature reaches zero. It stops because the field structure supporting the condensate reaches its lowest configuration. Zero-point energy, the same principle that governs electrons and photons, sets a limit on how quiet the system can become. Further demonstrations came from experiments involving vortices in rotating condensates. When scientists gently stirred the condensate using laser beams, vortex lines formed, each representing a tiny whirlpool of circulating atoms. These vortices were arranged in orderly lattices, a pattern that emerged only because the condensate moved as a coherent whole. The formation of vortices provided irrefutable evidence that the condensate possessed internal motion governed by quantum rules, not by temperature. The Cold Atom Lab aboard the International Space Station later added a new dimension to this research. Without the influence of gravity, atoms remain suspended rather than compressed at the bottom of the trap. This allows researchers to study condensates over longer periods of time. In microgravity, condensates expand more slowly, revealing detailed structure that Earth-based laboratories cannot observe. NASA reports showed images of condensates holding their form for extended durations, displaying the steady coherence of the quantum wave. Even in orbit, near some of the lowest temperatures ever reached, condensates carried the same signature motion. The phenomenon also appears in astrophysical contexts. Neutron stars, for example, contain matter at densities far greater than anything achievable in a laboratory. In certain layers of these stars, neutrons may behave like a condensate, forming coherent quantum states that influence the star's rotational properties. While these environments are vastly different from laboratory traps, the underlying physics is similar. Coherence replaces stillness. Quantum structure guides behavior even under extreme conditions. The discovery of Bose-Einstein condensation also illuminated how quantum mechanics transitions from the microscopic to the macroscopic world. Normally, quantum effects appear only at atomic scales. In a condensate, the wave function extends over distances visible to the human eye. Scientists at Gila and MIT measured condensate sizes on the order of tens of micrometers, a domain large enough to observe directly. This expansion marked one of the first demonstrations that macroscopic objects can behave according to quantum laws under the right conditions. Behind these breakthroughs lie years of incremental progress. Cooling atoms with lasers required precise control of atomic transitions. Magnetic traps had to be shaped carefully to prevent atoms from escaping. Detectors needed to capture images with enough contrast to distinguish condensates from thermal clouds. Each refinement brought researchers closer to the threshold where condensates formed. When the breakthrough finally came, it reshaped how physicists understood matter at low temperatures. Measurements across the coldest regimes show that even the condensate cannot be taken as proof of stillness. Lower temperature removes the thermal activity that masks the underlying structure, allowing the ground state of the system to become visible. In this condition, atoms move in a coordinated pattern shaped by the symmetries of the field that defines the condensate. What emerges is not absence of motion, but a form of order that only appears when thermal effects are nearly gone. As coherence in these condensates becomes clearer, the progression into deeper cold expands toward a domain where attention shifts from motion to the meaning of time itself. carrying the exploration into Part 6. If movement never truly stops, what happens to time at 0 Kelvin? The most disorienting discovery in ultra-cold physics appeared when researchers cooled crystalline solids toward the lowest temperatures achievable and found entropy settling into a plateau where familiar thermodynamic gradients no longer behaved as expected. Measurements that should have shown a steady decline collapsed into a flat line, as if the directional flow that defines before and after had weakened until it could no longer guide the system. This insight began taking shape in the mid-20th century when cryogenic physicists studying materials such as solid helium, metallic alloys, and rare earth crystals pushed them into millikelvin conditions. These experiments relied on adiabatic demagnetization, a technique in which magnetic fields are slowly reduced while the system is isolated from external heat. As the temperature dropped, scientists monitored entropy through specific heat measurements. In classical thermodynamics, entropy should decrease smoothly as a system becomes more ordered. Instead, the readings flattened. No matter how much the temperature was reduced, entropy refused to fall any further. This plateau raised questions for teams working at institutions such as the National Bureau of Standards, Oxford's Clarendon Laboratory, and cryogenic facilities in Moscow. Instruments were checked. Calibrations were repeated. Thermal leaks were hunted down. Yet the plateau persisted. It appeared in different materials, across continents, across redesigned equipment. The phenomenon was not experimental noise. It reflected something fundamental in the behavior of matter at low temperature. To understand why this challenged scientific intuition, it helps to recall how the flow of time is linked to thermodynamics. In physics, time gains direction from entropy. Systems evolve from states with fewer microstates to ones with more. Sean Carroll expressed this by saying, "Time is what entropy does. If entropy stops changing, the thermodynamic arrow that distinguishes past from future weakens." The experiment suggested that when temperature approaches 0, the system loses the gradients that allow time to express itself in physical processes. Cryogenic physicists observed this through relaxation experiments. After cooling a crystal to millikelvin temperatures, researchers perturbed the system slightly and recorded how long it took to settle into equilibrium. At higher temperatures, relaxation was fast. But below a threshold, the relaxation times grew longer and longer until they stretched beyond the duration of the experiment. It was as though the system no longer carried a clear preference for evolving in one direction. Instead of drifting steadily toward equilibrium, the system lingered. The boundary between past and future blurred. One of the earliest documented examples came from studies of paramagnetic salts. When these materials were cooled, using adiabatic demagnetization and held near 0.01 Kelvin, researchers expected entropy to continue decreasing. Instead, heat capacity measurements indicated that the number of accessible microstates had reached a limit. The arrangement of magnetic moments no longer changed with temperature. This meant the system was no longer generating the microscopic rearrangements that anchor the flow of thermodynamic time. Around the same period, solid helium provided another case. In helium-3 and helium-4 solids, nuclear spin arrangements contribute to entropy. But when cooled to extreme limits, the spin systems locked into configurations that barely changed. Nuclear magnetic resonance experiments showed relaxation times stretching into hours. The spins were still active, in quantum terms, but their contribution to entropy no longer varied. The system had reached a plateau where temperature offered almost no leverage. As cryogenic technology advanced, dilution refrigerators extended the range of achievable temperatures into the micro-Kelvin domain. These instruments relied on phase separation between helium-3 and helium-4 to extract heat efficiently. They offered unprecedented stability, allowing researchers to push the entropy plateau to even lower temperatures. But the core phenomenon remained unchanged. The closer the system approached absolute 0, the less entropy changed. Without entropy gradients, the thermodynamic timeline weakened further. Quantum field theory offered a broader framework for understanding this effect. At low temperatures, a system is restricted to its lowest available energy configurations. When all higher energy microstates become inaccessible, the system cannot explore new arrangements. With no additional microstates to occupy, entropy becomes constant. In this scenario, time defined through thermodynamic change loses its operational meaning. The system still evolves microscopically. Wave functions shift, quantum fields fluctuate, but the macroscopic signature that gives time its arrow fades. Researchers at Los Alamos and MIT observed this phenomenon in metallic glasses cooled to millikelvin regimes. These materials contain disordered atomic arrangements that typically support a wide distribution of energy states. Yet at ultra-low temperatures, the distribution narrowed drastically. Relaxation processes froze out. Internal rearrangements slowed until they became immeasurable. Even though quantum motion remained, entropy approached a flat boundary. This boundary gave the appearance that time itself had slowed. Another example came from experiments involving nuclear spin polarization in helium-3. When the spins were aligned in strong magnetic fields and cooled to micro-Kelvin temperatures, they behaved collectively in ways that resisted change. The system reached what physicists called a spin-ordered state. In this condition, entropy was minimal and stable. Attempts to drive the spins into new configurations required energy inputs far larger than expected because the system could no longer follow the usual thermodynamic pathways. The more data accumulated, the clearer the connection became. At high temperatures, time flows easily because entropy increases readily. At low temperatures, accessible microstates shrink. At temperatures near absolute zero, the system reaches a point where entropy becomes fixed. When entropy no longer changes, thermodynamic time loses traction. The experiments did not stop time. They simply revealed a regime where time, as defined by macroscopic change, ceased to provide useful guidance. Observations from astrophysics offered an unexpected parallel. ESA's Planck mission measured variations in the cosmic microwave background, the cold relic radiation from the early universe. These variations trace the distribution of density in the infant cosmos. As the universe expands, the temperature of this radiation falls, but the rate at which structure evolves also slows. In the far future, as the background cools further, models predict that the universe will approach a thermodynamic state where entropy gradients weaken dramatically. The cosmos would not freeze in a literal sense, but the large-scale thermodynamic processes that give time its direction would become faint. Historical accounts reveal how strongly these findings affected the researchers involved. Cryogenic laboratories invested years into perfecting isolation techniques, stabilizing magnetic fields, suppressing vibrational noise, and refining thermometry. When entropy plateaus first appeared, teams suspected instrument drift, sensor saturation, or stray heat leaks. They repeated measurements across multiple labs. The plateau remained. As physicists compared results internationally, the conclusion solidified. The plateau reflected a boundary of thermodynamic behavior, not experimental error. This realization changed how scientists conceptualize the approach to absolute zero. They no longer picture a smooth descent into perfect order. Instead, they see a landscape where entropy becomes trapped at a minimal value, and where the familiar markers of time weaken. Absolute zero is not simply a point of extreme cold. It is a boundary where the mechanisms that drive macroscopic change become limited. At this boundary, microscopic motion remains. Quantum fluctuations persist, and atoms, along with their spins, continue to shift within the narrow limits set by the ground state. Entropy no longer determines these behaviors. When entropy ceases to change, the thermodynamic definition of time loses its usual meaning. The data do not indicate that time ends. They show that the version of time connected to macroscopic evolution no longer applies in the same way it does at higher temperatures. The evidence forming at this plateau brings the next stage into view, extending the exploration toward the limits of physical law and setting the transition to Part 7. Would the laws of physics break if absolute zero were somehow reached? The most unsettling realization in modern cryogenic research emerged when physicists tried to calculate what it would take to cool any system to exactly 0 Kelvin, and found that the final step demanded an infinite level of precision no laboratory could ever achieve. Every experiment, every equation, every refinement pointed toward the same conclusion. To reach absolute zero, One would need to eliminate the last remaining quantum fluctuations, yet those fluctuations arise from the structure of the vacuum itself. At the Massachusetts Institute of Technology, researchers at the Laboratory for Extreme Quantum Systems pushed matter into temperatures measured not just in microkelvin or nanokelvin, but approaching the picokelvin regime. Their experiments used magnetic traps, evaporative cooling stages, and finely tuned laser systems to remove nearly every trace of thermal motion. As the temperature fell, the atoms settled into narrower energy distributions. But when scientists tried to push further, the cooling curve flattened. No amount of refinement produced progress beyond a certain limit. This limit followed from a principle rooted in the third law of thermodynamics. At low temperatures, entropy decreases rapidly. But as the temperature approaches zero, entropy approaches a constant minimum. Reaching absolute zero would require eliminating every accessible microstate, a task that demands infinite work. The last fraction of energy cannot be extracted because the system has no remaining path to release it. The researchers at MIT confirmed this through direct measurements of heat capacity and energy level spacing in ultra-cold atom clouds. Every drop in temperature required exponentially greater effort. The microscopic reason for this impossibility originates in quantum mechanics. Particles are not solid dots of matter. They are excitations of fields, and these fields possess unavoidable fluctuations even in their lowest energy configurations. These fluctuations form zero-point energy, the same phenomenon observed earlier in the Lamb shift, the Casimir effect, and cavity quantum electrodynamics. Removing zero-point energy is not like removing thermal energy. Zero-point energy defines the ground state of the field. Attempting to eliminate it would mean trying to remove the structure that allows particles to exist. This is where the remark by John Wheeler becomes deeply relevant. He stated, "The universe does not permit infinite answers. Reaching absolute zero would require measuring and cancelling quantum fluctuations with infinite accuracy. Any finite measurement leaves behind a residue. That residue keeps the system above 0 Kelvin." Wheeler's phrase reflected the mathematical reality that nature protects certain boundaries. Absolute zero is one of them. Stories from the MIT experiments illustrate how this limit manifests in practice. In one series of tests, physicists trapped potassium atoms inside a precisely shaped optical lattice and lowered the temperature toward 500 picokelvin. At this point, the atoms entered extremely narrow energy bands. Reducing the temperature further required a method called sympathetic cooling, in which one species of atom is cooled and carries other species with it. Yet, when researchers applied this method, the cooling nearly halted. The atoms began sampling only the lowest available quantum states. No pathway existed to shed the final energy. The experimental logs from this period show long hours spent testing new configurations, each producing smaller and smaller temperature improvements until the curve refused to move. Quantum simulations performed alongside the experiments helped explain the plateau. When the energy distribution shrinks sufficiently, the system becomes dominated by zero-point motion. The atomic wave function spread out according to the rules encoded in the underlying field. Even if thermal energy is removed completely, the wave functions cannot collapse into a configuration with zero momentum. If they did, their positions would need to be perfectly defined. That would violate the uncertainty principle. The universe prevents a system from entering such a state. Other laboratories around the world confirmed these findings. At the University of California, experiments with superconducting qubits showed that fluctuations in the electromagnetic field persist even at the lowest operational temperatures. At Cornell, measurements of ultra-cold fermionic gases demonstrated that particles continued to exchange momentum through quantum tunneling. In Japan, cryogenic facilities studying spin systems found that nuclear spins retained baseline activity even when thermal contributions became negligible. Each experiment reinforced the same boundary. One particularly revealing example comes from attempts to cool Bose-Einstein condensates in microgravity environments. Aboard the International Space Station, NASA's Cold Atom Lab reduced temperatures using improved evaporative cooling protocols. Without gravitational compression, atoms could remain in traps long enough to achieve lower temperatures than possible on Earth. Yet even these extraordinary conditions encountered a limit. As the temperature approached the lowest achievable value, the condensate stopped shrinking in energy width. The remaining motion reflected the quantum structure of the atoms rather than temperature. A similar boundary appears in cosmological models. ESA's Planck mission revealed that the cosmic microwave background temperature has been decreasing since the formation of the universe. Yet theoretical models show that the temperature will approach zero asymptotically without reaching it. This occurs because vacuum energy persists. Even in a universe stretched by cosmic expansion across trillions of kilometers, zero-point fluctuations remain. They define a baseline temperature that cannot be erased. When these findings are viewed as a whole, a coherent theme emerges. The final approach to absolute zero is obstructed by the same rules that govern electron shells, photon momentum, and atomic wave functions. Reaching zero would require flattening the quantum fields that define particles and interactions. That flattening is impossible because the fields contain intrinsic oscillations that persist regardless of external conditions. Removing them would violate the mathematics of quantum theory, the symmetry principles that guide particle interactions, and the uncertainty limits built into the structure of space. Historical attempts to reach absolute zero underscore how deeply this boundary is embedded. In early cryogenic laboratories of the 1930s and 1940s, researchers believed improved refrigeration would eventually reach the limit. Liquid helium, adiabatic demagnetization, and dilution techniques each reduced temperature dramatically, but every new milestone revealed a steeper curve. Eventually, the third law of thermodynamics crystallized the pattern into a formal statement. Absolute zero is unattainable through a finite sequence of steps. Modern equipment has pushed far beyond the limits those early scientists imagined. Superconducting circuits now operate at a few tens of millikelvin. Ultra-cold atom clouds reach nanokelvin values. And specialized cryogenic platforms achieve picokelvin temperatures. Yet, despite this extraordinary progress, the boundary remains as firm as ever. Nature offers no mechanism to erase zero-point energy. The universe enforces the rule that some motion always survives. The implications extend into fundamental physics. If absolute zero could be reached, quantum fields would lose their foundational fluctuations. Atoms would collapse into perfectly defined states. Photons would cease to behave as excitations of an electromagnetic field. Particles would no longer interact through exchange processes. In short, many of the phenomena that allow matter, chemistry, and radiation to exist would disappear. The inability to reach absolute zero is not a shortcoming of technology. It is a safeguard that preserves the structure of the world. Every experiment probing deep cold, from MIT's quantum systems to NASA's microgravity platforms, has reinforced the same outcome. No matter how advanced the cooling method becomes, the temperature approaches zero only asymptotically. The final step remains inaccessible because reaching absolute zero would require removing every form of microscopic motion, an operation that demands infinite precision. John Wheeler captured this limitation in a single line: "The universe does not permit infinite answers." And 12th, the behavior observed near this limit reveals a new landscape, directing attention toward the transformations that appear as matter approaches extreme cold and preparing the transition to Part 8. Why does superconductivity appear when matter approaches the deepest cold? The moment researchers cooled certain metals toward the lowest temperatures they could produce, the electrical resistance that should have remained finite collapsed abruptly to zero, as if electrons had slipped into a different form of behavior altogether. This sudden disappearance of resistance, first observed at Bell Labs and later refined through NASA-supported material studies, revealed that deep cold unlocks patterns of motion that cannot exist when thermal agitation dominates. The earliest breakthrough occurred in the 1950s, when experimentalists studying mercury found that its resistance dropped sharply once it cooled below a threshold temperature. The equipment available at the time was crude by today's standards, yet the effect was unmistakable. Current flowed through the sample without producing heat. No energy was lost. This was not simply a matter of reducing resistance. It was the complete removal of it. Physicists soon realized that ordinary electrons could not explain the phenomenon. In typical metals, electrons scatter off impurities, lattice vibrations, and other electrons, creating resistance. For resistance to vanish, electrons would need to move without scattering, something individual electrons cannot do. The solution came in the form of paired states. Instead of acting independently, electrons near absolute zero form linked partners now known as Cooper pairs. These pairs behave not as separate particles, but as a coherent quantum state extending across the material. Once formed, Cooper pairs move with remarkable stability. Thermal motion, which normally disrupts electron paths, is too weak at ultra-low temperatures to break the pairing. The electrons glide collectively through the lattice. Because they share a unified quantum state, scattering events that would deflect individual electrons no longer apply. The material transitions into a superconducting phase where current experiences no resistance. Stories from the early experiments capture the sense of confusion and then clarity as the phenomenon unfolded. At Bell Labs, engineers repeatedly checked their instruments, unsure whether the resistance drop was an artifact. They heated the sample, cooled it again, replaced wiring, and recalibrated sensors. Each time, the same sharp transition appeared. The data convinced them that something in the structure of matter had changed fundamentally. The concept gained further support when scientists observed the Meissner effect. When a superconductor forms, it expels magnetic fields from its interior. This behavior suggested that superconductivity represented not just a reduction of resistance, but the emergence of a new order. The system reorganized itself into a state that rejected disturbances, reinforcing the idea of coherence at the atomic scale. As cryogenic technology improved, superconductors were cooled with liquid helium and later with dilution refrigerators, achieving temperatures far lower than earlier experiments. These conditions allowed researchers to investigate the microscopic structure of superconductivity. Using neutron scattering, muon spin rotation, and tunneling spectroscopy, they observed how Cooper pairs formed energy gaps within the electronic structure of the material. These gaps prevented electrons from scattering in ways that would break coherence. NASA's involvement came through the study of superconducting materials for applications in magnetic levitation, satellite gyroscopes, and high-precision sensors. Materials tested under controlled cryogenic environments displayed consistent transitions into superconducting states, revealing the robustness of the phenomenon. These studies confirmed that the absence of thermal noise allows quantum coherence to dominate, enabling electrons to coordinate motion over macroscopic distances. High-temperature superconductors added another layer to the story. Discovered in the 1980s, these materials exhibited superconductivity at temperatures far higher than traditional metals, sometimes reaching above 100 Kelvin. Although they still required cooling, the mechanisms allowing superconductivity to persist at these temperatures remained the subject of intense research. Advanced imaging and spectroscopy revealed intricate patterns within the crystal lattice that supported unconventional pairing states. These findings showed that superconductivity was not a rare quirk, but part of a broader spectrum of quantum behavior emerging when noise is stripped away. One of the most compelling demonstrations of coherence in superconductors comes from persistent currents. When a superconducting ring is set into motion with an electric current, the current flows indefinitely. Experiments have shown these currents continuing for years without measurable decay. This persistence arises because the quantum state describing the Cooper pairs is stable and uniform. Once established, the state cannot dissipate energy through classical pathways. Further insights come from Josephson junctions, narrow barriers separating two superconductors. In these devices, Cooper pairs tunnel through the barrier, producing oscillations in current that depend on the energy difference between the two sides. The oscillations are so precise that Josephson junctions became part of standards for voltage calibration. Their behavior reflects quantum coherence on a scale large enough to support technological applications. Experiments with superconducting qubits used in quantum computing take this idea even further. These qubits rely on quantum states within superconducting circuits that retain coherence for long periods when properly isolated from noise. Although not perfect, their stability depends on the same principles that govern superconductivity: minimal scattering, strong pairing, and ordered motion. Research at MIT, Google Quantum AI, and other institutions continually shows that deep cold exposes patterns of quantum order that classical conditions cannot reveal. Astrophysical observations provide a fascinating parallel. Neutron stars contain matter compressed to densities that force electrons and protons into extreme configurations. In certain layers of these stars, conditions may allow superconductivity at temperatures far above those found in terrestrial labs due to the intense pressure. Models of neutron star interiors suggest that electrons form paired states similar to Cooper pairs, allowing currents to flow with minimal resistance. These currents may influence magnetic fields and rotational behavior. Although these environments differ profoundly from laboratory conditions, the underlying coherence remains relevant. Superconductivity also expands our understanding of quantum identity. In metals at ordinary temperatures, electrons behave largely as independent particles. But as thermal agitation fades, the mutual relationships between electrons become clearer. Cooper pairing reflects the collective nature of the quantum world, where individual behavior gives way to synchronized patterns. The lattice vibrations that ordinarily scatter electrons transform into participants in the pairing mechanism. Even impurities can be absorbed into the dynamics of coherence if conditions are suitable. Every stage of cooling reveals another layer of structure. At high temperatures, vibrations overwhelm any possibility of coherence. At intermediate temperatures, electrons begin to sense collective constraints. Near absolute zero, coherence dominates entirely. The material behaves as a single, ordered entity, not as a disorganized ensemble of particles. Superconductivity represents one of the clearest examples of how quantum physics shapes the macroscopic world. Behind these discoveries are decades of persistence. Experimentalists built cryostats from scratch, designed instruments capable of measuring minute voltage changes, and examined countless materials for signs of superconductivity. At Bell Labs, the early pioneers confronted readings that seemed too clean to believe. At NASA facilities, materials were tested under vacuum, in orbit, and within chambers designed to eliminate interference. Through each effort, the same principle emerged. When matter is stripped of thermal noise, quantum order asserts itself. Data from superconducting systems illustrates a broader truth about deep cold. These temperatures do not slow particles into stillness. They remove fluctuations that mask long-range coherence. In this environment, electrons begin to act collectively, currents persist without energy loss, and the distinction between microscopic behavior and macroscopic effect becomes narrower. Superconductivity is not a reduction of motion. It is the appearance of coordinated behavior that emerges when thermal influences are almost entirely removed. As these patterns become clearer, the progression into deeper regimes of cold extends toward the field's underlying matter itself, setting the transition to Part 9. Could absolute zero reveal the true structure of the quantum vacuum? The moment researchers aboard the International Space Station cooled clouds of atoms to within billionths of a Kelvin above absolute zero, their detectors recorded subtle distortions in the surrounding quantum fields, signals so faint and ordered that they matched predictions from quantum electrodynamics made decades earlier. What should have been the quietest environment ever created by humanity, instead, became a stage where the underlying structure of spacetime revealed patterns ordinarily buried beneath thermal noise. Inside NASA's Cold Atom Lab, atoms trapped in magnetic and optical fields were brought to temperatures unimaginably low. On Earth, gravitational forces press atomic clouds against the trap, limiting the time available to observe them. In microgravity, the atoms remain suspended, allowing far longer measurements and cleaner isolation. When cooled to around 1/1000th of a Kelvin, their wave functions expanded, becoming large enough for instruments to detect faint interactions between the atoms and the vacuum itself. Quantum electrodynamics predicts that even what appears to be empty space is threaded with fields. These fields fluctuate continuously at all energy levels. At ordinary temperatures, such fluctuations are overwhelmed by thermal motion. But in the deep cold of the ISS experiments, that motion nearly vanished. What remained was the vacuum's own activity. Researchers noticed tiny shifts in atomic energy levels and movement that did not arise from the atoms themselves, but from the vacuum's oscillations. These effects aligned with several long-standing QED calculations, vacuum shifts, field, induced energy corrections, and modifications of scattering behavior. To understand why this is possible, consider what happens as temperature plummets. The kinetic energy of atoms decreases, their momentum narrows. As the cloud cools, the atoms begin occupying the lowest available energy states. Here, quantum behavior dominates. The wave function of each atom widens, increasing its sensitivity to external fields. At the lowest temperatures ever produced, the atoms respond not to collisions or thermal agitation, but to vacuum fluctuations predicted by theory. These fluctuations can slightly push, pull, or alter atomic states, leaving measurable traces. One of the earliest hints that the vacuum had structure came from the 19th century discovery of blackbody radiation, which showed that energy could not vary continuously. Later, experiments such as the Lamb shift revealed that energy levels in hydrogen atoms deviate slightly due to interactions with vacuum fields. In the mid-20th century, the Casimir effect demonstrated that two neutral plates placed extremely close together experience a measurable force caused by the vacuum's fluctuating fields. Each discovery pointed toward the same conclusion. Empty space is not empty. It is active. The Cold Atom Lab provided a setting where these effects could be examined with unprecedented clarity. When researchers manipulated rubidium atoms into Bose-Einstein condensates and then brought temperatures even lower, the condensates stretched. Their density distributions shifted in ways that indicated the atoms were responding to external fields beyond the trap. These shifts had not been visible in earlier experiments conducted on Earth because gravity and ambient noise overwhelmed the signal. In orbit, the clarity improved dramatically. In several runs, the atomic clouds expanded more than predicted by standard models, a sign that vacuum fluctuations contributed to the dynamics. A story from the Cold Atom Lab team illustrates the gradual realization. After months of calibration, the first stable nanokelvin cloud was recorded. The team expected the expansion of the cloud to follow a clean, mathematically simple curve. Instead, tiny deviations appeared at predictable frequencies. The researchers repeated the experiment across multiple cycles with varied trap geometries. Each time, the same deviations appeared. It was not instrument noise. It was the vacuum imprinting itself on matter. Quantum field theory explains this behavior by describing the vacuum as a collection of energy modes. When atoms reach extremely low energy states, they interact with these modes as though touching a vast underlying fabric. The structure of this fabric is smooth at large scales, but textured at microscopic ones. In ultra-cold environments, atoms become sensitive to this texture, and their wave functions deform slightly in response. Researchers compared these distortions with predictions from QED. One prediction involves vacuum polarization, where the vacuum behaves like a medium that slightly screens electric charges. Another involves modified dispersion, where the speed of light in vacuum changes minutely depending on quantum fluctuations. While the experiments aboard the ISS did not measure light's velocity, they did detect effects consistent with polarization patterns at microscopic scales. The agreement between theory and experiment strengthened confidence in the underlying physics. Cryogenic physicists on Earth had previously observed related effects at higher temperatures. In superconducting circuits operating at millikelvin levels, quantum noise remaining in the system originates from vacuum fluctuations. But in those environments, impurities and thermal photons introduce complications. In space, the cleaner environment produced measurements approaching theoretical ideals. These observations tie into another crucial phenomenon. In ultra-cold traps, atoms occasionally tunnel into energy states they should not reach according to classical physics. The probability of tunneling depends on the shape of the potential and vacuum fluctuations. Near absolute zero, tunneling patterns change in ways that match vacuum-driven predictions. The atoms behaved as though guided by minute ripples in the surrounding fields. Some experiments aboard the ISS explored how different trap geometries changed these interactions. When elongated traps were used, the clouds responded more strongly to field variations along one axis. When spherical traps were used, distortions were more symmetric. These results suggested that the atomic wave functions were sampling the vacuum differently depending on geometry. The pattern matched predictions from quantum field simulations run on Earth-based supercomputers. Another layer of insight came from comparing ISS data with astronomical observations. ESA's Planck satellite measured variations in the cosmic microwave background with extreme precision. These variations reflect the influence of quantum fluctuations stretched across cosmic distances during the early universe. The same physical principles appeared in both contexts. In the early universe, vacuum fluctuations imprinted patterns on primordial light. In the cold atom lab, vacuum fluctuations shaped microscopic atomic motion. The scales differ immensely, but the underlying mechanism remains unified. Historical accounts of early quantum theory show how revolutionary this idea once seemed. When physicists first proposed that the vacuum contained energy, many considered it too speculative. But as experimental techniques advanced, first through spectroscopy, then through particle accelerators, then through cryogenic systems, the evidence accumulated. Now, experiments in orbit, at temperatures that challenge imagination, continue this progression. The vacuum, once a philosophical concept, has become a measurable environment. The implications extend into several branches of physics. If the vacuum has structure, then space-time itself has a texture that influences particles. This texture is normally invisible because thermal motion overwhelms it. At nanokelvin scales, the texture becomes detectable. Deep cold becomes a tool not merely for studying matter, but for studying the fabric of reality. This also intersects with ongoing efforts to unify physics. For instance, quantum electrodynamics describes vacuum behavior for electromagnetic fields. Other theories extend similar principles to matter fields, gravitational fields, and beyond. The cold atom lab experiments do not test these theories directly, but they provide clean data showing that the vacuum's influence is real and measurable. Behind every result lies a story of precision and patience. The ISS crew monitored environmental stability. Ground teams adjusted magnetic gradients through remote commands. Data traveled across thousands of kilometers to Earth, where analysts compared the shapes of expanding clouds with theoretical curves. Many early tests showed noise or drift, but as calibrations improved, consistent patterns emerged. Each pattern echoed the predictions of quantum field theory. Evidence from experiments near absolute zero reframes how physicists think about cold. Extreme cooling does not immobilize the universe. It removes thermal activity and exposes a level of organization normally hidden at higher energies. Even in the most controlled conditions humans have achieved, the vacuum displays structure that remains active, defined by quantum fields rather than heat. With these results, establishing a link between temperature, quantum behavior, and space-time itself, the direction broadens toward the final stage of this exploration, setting the transition to Part 10. If the universe never reaches zero, what does that tell us about reality? The most far-reaching discovery in cosmology emerged when scientists realized that even as the universe expands and cools toward deeper and deeper cold, no calculation, no simulation, and no physical model permits its temperature to ever reach 0 Kelvin. Every dataset, every sky survey, every measurement from the oldest detectable light points toward the same conclusion. The cosmos approaches zero, but never touches it, as if a boundary woven into the structure of space-time prevents complete stillness from unfolding anywhere in existence. This insight began with measurements of the cosmic microwave background, the faint radiation that fills every direction of the sky. Its temperature today is about 725 Kelvin. When NASA's COBE satellite first mapped it in the early 1990s, the data confirmed that the universe had cooled dramatically since the era when matter and radiation separated. ESA's Planck mission later produced maps of even greater precision. These missions measured not only the average temperature, but the subtle variations imprinted by early quantum fluctuations. As cosmologists modeled the evolution of this background through billions of years of expansion, a pattern appeared. The temperature falls steadily, but always slows as it approaches zero. The reason follows from the physics of photon redshift. As space expands, the wavelength of each photon stretches. The energy drops and the radiation cools. Yet this cooling depends on the expansion rate, which decreases over time in a way that ensures the temperature approaches zero asymptotically. No matter how far into the future one looks, the calculations never reach a moment when the cosmic microwave background reaches absolute zero. Even after trillions of years, the universe retains radiation, however faint. This behavior is tied to the persistence of vacuum energy. Quantum field theory describes the vacuum as possessing fluctuations that cannot disappear. These fluctuations give the vacuum a baseline temperature that never becomes zero. When cosmologists include this energy in their simulations, the temperature curve of the universe flattens as it approaches the far future cold. The last fractions of a Kelvin cannot be removed because the vacuum prevents the universe from settling into perfect stillness. Observational evidence supports this view. In deep-field images captured by NASA's JWST, astronomers detect galaxies forming during the universe's early expansion. These galaxies emit infrared and microwave radiation that travels across billions of light-years, stretching with expansion but never ceasing. Even the most ancient photons discovered so far retain momentum. Their wavelengths may reach extraordinary lengths in the distant future, but they continue to exist. The universe never becomes silent. Cosmologists, studying models of the universe's ultimate fate, often consider heat death, a state where stars fade, matter spreads thinly, and energy gradients flatten across colossal distances. Yet even these models refuse to give the universe a temperature of 0 Kelvin. The presence of vacuum energy introduces a flaw. Fields cannot be pressed into perfect stillness. The cosmos grows colder, but not cold enough to erase their influence. A story from the development of early universe theory illustrates how surprising this result once seemed. When researchers began calculating the long-term evolution of the cosmic background, some expected the temperature to eventually reach zero. As simulations improved and included more factors, dark energy, gravitational expansion, quantum effects, the curve changed. It dipped lower but never reached the axis. Scientists checked their equations, refined their code, and compared models across different teams. The outcome remained steady. No version of the equations permitted zero. This outcome reinforced a thought shared by physicist Steven Weinberg, who wrote, "The universe is under no obligation to make sense to us." The long-term cooling pattern of the cosmos reflects this idea. The boundary is not intuitive. It emerges from the interplay of expansion, radiation, and quantum fields. The universe cools forever, but never completes the journey. Looking across cosmic history, the trend becomes even clearer. In the early universe, temperatures were unimaginably high. Particles collided with enormous energy. As expansion slowed, the temperature dropped rapidly. When the first atoms formed, the universe cooled to thousands of Kelvin. Later, as stars ignited and galaxies formed, pockets of heat reappeared. Yet the grand trend pointed downward. Over billions of years, starlight faded, galaxies drifted apart, and the background temperature dropped. Each step reduced motion on large scales. Yet none of it approached true stillness. The interplay between gravity and expansion also plays a role. Gravity pulls matter together, creating stars, galaxies, and clusters. Expansion pushes space apart, thinning matter and diluting energy. As the universe grows older, expansion dominates. The thinning background radiation shifts to longer wavelengths. The interactions that shape cosmic evolution become slower. But as long as the vacuum holds its energy, the universe cannot settle into a final, motionless state. Astrophysical observations confirm this. Across massive voids spanning hundreds of millions of light-years, radiation still permeates even the emptiest regions. Although this radiation is faint, it is never zero. Measurements from high-altitude balloons, ground-based microwave telescopes, and orbital observatories all point toward an identical conclusion. Every corner of space carries the imprint of a temperature above zero. Some theoretical models explore even deeper futures, when all stars have burned out and black holes evaporate through Hawking radiation. In these scenarios, the universe becomes increasingly cold. Yet even after black holes vanish, the vacuum persists. Radiation diminishes toward zero, but never touches it. The calculations describe a universe that becomes quieter and colder with each passing era, but the floor set by quantum fields remains. Behind these predictions lie decades of refinement. Researchers examined the expansion rate with Type Ia supernova measurements, calibrated cosmic distances with baryon acoustic oscillation data, and mapped matter distribution with gravitational lensing surveys. Each dataset contributed to the understanding of how temperature evolves. When combined, the models grew robust. And across all of them, the asymptotic boundary remained a defining feature. This boundary shapes how scientists view the nature of motion. If the universe can never reach zero, then motion, however faint, must always persist. Even at the largest scales, the cosmos carries fluctuations driven by quantum fields. This persistence echoes what experiments in ultra-cold laboratories revealed on microscopic scales. Atoms never reach stillness, photons never reach rest, electrons never fall into silence, and the universe mirrors their behavior. Instead of a cosmos drifting toward perfect quiet, we find one governed by limits that prevent stillness from ever arising. The boundary protects the structure of matter and the behavior of fields. It ensures that interactions remain possible and that space-time retains measurable features. The impossibility of absolute zero is not a failure of cosmology. It is a foundational rule embedded in reality. This final insight brings the journey full circle. From atoms trapped in magnetic fields to cosmic radiation spread across billions of light years, cold reveals patterns that heat conceals. The deeper scientists explore, the more clearly these patterns appear. Absolute zero remains unreachable because the universe is built upon fluctuations that cannot be extinguished. Motion endures. And as this chapter closes, may your night be restful and calm. Thank you for spending this time exploring the coldest frontiers of physics. May sleep come easily, and may tomorrow greet you with curiosity renewed.